The rotated conics, by rotated I mean, in other words, the only thing we've discussed are up, down, and sideways parabolas. Any conic that is either vertical or horizontal like this will not have this term in it.
Okay, now any conic which is what will have not have the...
That is not at an angle. In other words, if it's either vertical or horizontal, it will only have these terms. You get a parabola that looks like this by having one of those in it, in the equation.
Okay.
Okay, and just as an example of that, an ellipse is x squared over a squared plus y squared over b squared equals 1. There's no xy term. There's an ax squared, and there's a cy squared, and there's an f. But that's it. And if I take the ellipse and move it, well, that was actually at the origin. That's the equation of an ellipse at the origin. But if I move the ellipse up here, keeping it horizontal, then I pick up one of those, and I pick up one of those. I still have the ax squared, and I still have the cy squared, but I also pick up other, and then I have to complete the square in order to come up with the proper equation. But in none of them do I have this xy term. And this xy term is the indicator that you're not looking at a horizontal or vertical ellipse. Or these can be any conic sections. This could be a hyperbola also. This is the general equation of parabolas, circles, ellipses, and hyperbolas.
Okay.
Okay. In other words, if I wanted the parabola y equal x squared, then I'm going to have this y term over here, and I'm going to have the x squared term, and I'm not going to have anything else.
Okay.
Okay. Now, let's see if I can remember where I'm going from this. Okay, so we have the Greeks intersecting planes with two cones, defining conics. We have algebraic definition of conics, and each one of these can be put into the general format. In other words, this is the general format for a parabola, this is the general format for an ellipse. We have similar things for circles and everything. But if I gave you a general second degree equation, you would be able to figure out what kind of a conic it was based on its signs and the existence of that and all of this stuff.
Okay.
Now, there's also what is called a degenerative conic. And if I go back and draw my two cones, boy, how the Greeks figured this out, I don't know. How would you know to start with this? You know what I'm saying? I mean, that had to be real out-of-the-box thinking. To start with two cones, one upside down with their vertexes together, and then start slicing it up to come up with these various things. Well, a degenerative conic is one where the plane goes through the vertex. In other words, if I slice that thing right there, I don't get a circle, I get an infinitesimally small point. If I slice it here, I just get a straight line. If I slice it there, I get a straight line. So anything that goes through the vertex, if the plane goes through the vertex, you end up with a degenerative conic. Now, what the implications of that are, I'm not sure.
Wait, how did the other two besides the point go? For the degenerative conics?
If you slice it right at the vertex,
yeah.
that's just going to be a point.
Right. And then there were some other ones?
Well, you would get a line if you sliced it this way.
It seems like that would be a hyperbola, unless I'm looking at it wrong.
Here, let me remember this page because we're going to get to this in a second. I didn't want to lose this page number. Let me write it down. 549. That's where we want to get back to. But I'm going to try to show you the pictures because I can't draw them good enough.
I got you.
Okay, the top, gosh, this thing is so sensitive. I can't hardly touch it without, okay. The top four are non-degenerative conics. In other words, that's how we get our circle, that's how we get our parabola, that's how we get an ellipse, and that's how we get a hyperbola. Remember, we're intersecting these things with a plane.
Oh, I think I see.
Now, the degenerative conic, we get just the point. And if the plane is at an angle that's not at the edges, in other words, that didn't go through there, it went through a corner of the upper cone.
Yeah, I think I see how it is. Just went along the edges there, but not...
Right, so the only thing that shows up is a line, and if the plane goes right down the middle, perpendicular, you get two intersecting lines, none of which are conics. A point, although I suppose you could argue that why is this degenerative? Isn't that just a circle of radius 0?
Yeah, right.
And today, reviewing this, I wouldn't have been able to tell you what a degenerative conic was. And I'm still not sure I can tell you what the equation of a degenerative conic looks like. I would imagine that you can't put it in the general format. And that would be indicative of a degenerative conic. I don't know. We'll maybe learn that. Okay, so let's see. So here's the second degree equation that I wrote out. This is the algebraic way of looking at any of the four conics. And there's a third approach in which each of the conics is defined as a locus, collection of points, satisfying a certain geometric property. And this one says that that way works best. For example, a circle can be defined as a collection of all points that are equidistant from a fixed point, the center. And the way I just defined the parabola was a parabola is a collection of points that are equidistant from a focus and a directrix. No matter where you're at on the parabola, that distance is going to equal that distance. If you're down here, this distance is going to equal this distance. Up here, that distance equals this distance. Okay? So all of these four conics can be defined as a collection of points with some geometric property. What happens if we go down one page? 697 now. And here's the equations that I was talking about. If it's the vertical axis, it's this. If it's a horizontal parabola, the key difference that I remember is that vertical parabolas are y equal x squared. In other words, the x is squared, the y is not. Horizontal is the reverse. The x is not squared, the y is. So an equation, a simple equation for a horizontal parabola would be x equal y squared instead of y equal x squared.
Okay.
Let's table that for a moment and go back to the page, the 549. Let's see, I can type that in, I think. Yeah. Now, this section here is the part of the book where we learned how to do trig substitution, solve integrals by trig substitution.
Oh, wow. Yeah, I barely remember.
It's hard. It's really hard. I would have to look it up. In order to be able to tutor it right now, I would have to do some review. Just because it took me 2 years to understand it. Finally, when I understood it, I did, but it's been a long time. I'll bet I haven't tutored it to anybody since you. No, because this isn't, you don't have to be able to do integration by trig substitution for the Calc BC AP exam. That's not on there. Oddly enough, because there's, as we know, there's plenty of stuff from Chapter 10 on there that we haven't covered yet. And yet this was in the book, but not part of the AP exam. The reason I'm showing you this is because it ends up that if you can get an integral into one of these three formats, then using the methods of trig substitution, this is the answer.
I see.
Now, one of the things you and I never really got into was using tables for integration. There's a whole section or chapter, not a full chapter, but a section on how to do that. And I didn't get into it because it seemed to me like it would be like studying the dictionary, you know. In other words, all we would be doing is looking at certain types of integrals and what they integrate to. Well, these three down here are fairly special. Notice why. It's the integral of the square root of a squared minus u squared, or u squared minus a squared, or u squared plus a squared.
What are a and u here? Just
use the variable, because they're all being integrated with respect to u. And a is just a constant. So if you had the integral of the square root of 4 minus x squared, then a would be 2, u would be x, and that integral would be equal to this. And you would substitute 2 for a and x for u, and that would be your answer for that integral. And the only reason I'm showing you this is because we're going to look at a problem today that is very tricky to integrate, and I guess the best way for me to even talk about it is to let's do it. If we have the simple equation x squared equals 4py. Okay? That's a vertical parabola because it's y equal x squared, not x squared equal y. And the problem is to we know a couple of other things about the focus. Not only is the focus the P from the vertex, but they have this thing called the Latus Rectum. I never figured out why math is so anal, but it seems to be. Got a lot of words in it that are very anal. In fact, the newer math courses don't call this the Latus Rectum, and you can imagine why.
Yeah.
Think of a class of juniors and seniors. The Latus Rectum, okay. Yeah, so they call this the focal width now. But that's what focal width is the same as, is the Latus Rectum. And this happens to be 4p. Okay.
All the way across.
Mm-hmm.
Okay.
Okay, and which makes this point right there 2p, comma p, and this point over here minus 2p, comma p, are the coordinates of those points.
Okay.
And the question is to find the arc length from this point to this point.
Oh, I see. Okay.
Okay, so if you'll remember, and this was also, arc length is also something I don't believe is covered on the AP exam.
Wait, that's not 4p? I mean, we're trying to find...
No, 4p would be the distance, the horizontal distance between there and there. Okay. We're trying to find the length of this arc.
Oh, the arc, okay.
In other words, if we had this made out of string, and we wanted to know the length of this string right there, that's a calculus problem. Arc length is a calculus problem. And if you'll remember, it ends up being a rather strange looking formula. It's 1 plus dy over dx squared dx.
This is a formula for arc length?
For any arc length. Or square root of 1 plus dx over dy squared dy. From A to B on the x-axis, or from C to D on the y-axis. These are the general formulas for arc length. Okay? Now, we're going to use this one. And we're going to go from minus 2p to plus 2p. So our arc length, which we'll call S, is going to be equal to that. And specifically, because of the symmetry, I can let it be equal to 2 times the integral from 0 to 2 pi, or 2p rather, of the square root of 1 plus, well, what is dy dx? If I solve this for y, I get the 4p down there.
But I kind of got, let's see, we had, where'd the 2 come from?
In other words, I was going from minus 2p to 2p,
Oh, I see.
but because of symmetry, I can make that 2 going from 0 to 2p.
Okay.
Can't always do that, but if it's symmetrical about the y-axis, you can. So now we have to figure out what dy dx is. So if this is y, what's dy dx?
Let's see, what was y now?
Y is this.
Oh, I see, okay. All right. Okay. Since y is x squared over 3, squared over 4p, and we're trying to find dy dx.
So just use the power rule. It's not a quotient rule because remember p is a constant. P is not changing here. P is based on the formula.
So it would be 4p times x cubed over 3?
Well, it would be 2x over 4p.
Jesus, what did I do? Oh, I was integrating, I think, not differentiating. Yeah, okay, so it's you differentiate and you get 2x over 4p?
Which is the same as x over 2p. Okay. Now is where it gets tricky. Let's see if I can figure out what they've done here, because it's not. I mean, and they did the same thing with when they derived the formula for surface area or length of an arc. Remember the length of an arc was harder to derive than the volume of three-dimensional objects or the area under the curve or any of that. Finding the length of an arc, the process that they went through was what I felt at the time was two-variable calculus. Let's just review that briefly. We may not get to the end of this problem today. But if I wanted the length of an arc, I'm going to break it up. Every single point is going to be dy, a dx, and that little hypotenuse. The length of the arc would be the square root of dx squared plus dy squared.
Okay, I think
in other words, if I circle in on that little point right there, I end up with a triangle, a right triangle, where this is delta x, this is delta y, and this is the length of the arc, which is the square root of delta x squared plus delta y squared. So that's the way they started out, trying to figure out how you get the calculus of a line. Of course, and then we're going to add all these tiny little segments up. In other words, the length of this line is made up of the millions of microscopic sections that each can be broken down into that.
Okay.
That's the theory behind finding the length of an arc. And then you add them all up, so you get an integral.
Okay.
It turns out that the algebra is very, very clever. I'd like to go over it again, although this problem we're going to do does similarly kind of go over it again.
Okay.
All right, so let's see. The next step they do. And remember our goal. Our goal is if we can get an integral to look like one of these three integrals down here, we know what its result is. These are special integration formulas. And they're particularly useful with finding arc lengths. So we want to end up with...
Were these special... Oh, I thought these were formulas for trigonometric substitution.
They derive from that. In other words, using trigonometric substitution is how we end up being able to get these three formulas. Okay. But suffice it to say at the moment that if we can get an integral into one of these three formulas, then we can use these formulas to get the answer.
Okay.
So that's going to be our goal here, is to translate this integral into something that looks like either a squared plus x squared, or a squared minus x squared, or x squared minus a squared, all under the radical sign. So how do we take this and accomplish that? Well, let's see if we can figure this out. What I've written there happens to be equal to this. And this is one of those little tricks, very, very similar trick that they use to come up with the formula for arc length in the first place. Notice that I've gotten it into something that resembles 3. U squared plus a squared.
Okay.
This is going to be the u squared, this is the a squared. That's a perfect square. That's 2p squared. Okay?
All right.
So the question is how do we get from this step to this step, which in the book they merely say simplification.
Wow.
It's easy enough to get from this step, the bottom one, to the top step, because all I got to do is take that constant, put it back inside the integral sign,
okay,
put it inside the square root sign.
Now, how do you put it inside the square root
By
sign?
squaring it. In other words, when I put it inside the integral sign, it goes to this.
Okay.
Now if I want to put it inside the radical, I got to square it, right?
Oh, I see. Okay.
So
Yeah,
I would have 4p squared divided by p squared, because I'd have to square it to put it in the radical, plus x squared divided by p squared.
Yeah, okay, okay.
Notice that's very close to this.
Okay, yeah.
Well, how do I get this out of this? Well, let's put the 2 back in. If we put the 2 back in and put it inside the radical, it becomes 4 plus 2 x squared over 2p squared.
Yeah, although it would distribute across each term, right? So it'd be 4 plus 4 times x squared over...
Now, the fact that this whole thing's being squared, let me think.
4 plus, so would it be 4 plus 4x squared over...
Think for a moment if I can figure out how to explain this better. If I put this 2 back in the radical, got to go in like this.
Yeah.
Now there's a product inside the radical. You can always take the square root of one of those. In other words, if I had this, I'd be able to take that 4 out as a 2. Okay? So put the 2 back in, it's got to look like that.
Okay, okay.
And now distributing that becomes the square root of 4 plus 4 times x over 2p squared, right?
Okay. Yeah.
Okay, well, if you square x over 2p squared, you get x squared over 4p squared. The 4's cancel.
Mm-hmm.
So I end up with x over p squared.
Okay. Yeah, x squared, p squared. Right, right.
So,
Oh, I see. So it does,
yeah,
because you had 4p squared over p squared, so that ends up being equal to
right. In other
4
words,
plus
whatever we
x squared
had,
over p squared.
we can't change it. It has to be the same. What they basically
Okay.
did was they started there. Well, no, I mean, this is pretty clever algebra. It's not, usually you take numbers out of this, but in this case, they're putting numbers in.
Okay. I got
They
you.
took this 2 that came from the symmetry of the parabola and put it inside the radical sign so that they could somehow come up with one of these situations over here.
Okay.
Okay? And they do that, and so when they simplify this, they end up with 1 over p times the square root of 4p squared plus x squared.
Okay. That makes sense. I think
Yeah, I mean, it's difficult to do it, but it definitely makes sense. In other words, if somebody has done it for you, you can verify that this is the same as this.
Okay.
Okay?
Makes sense.
And now we can use our formula. Whoa. Hold on. Okay. Our formula says, since we're looking at a squared plus u squared,
Okay.
we can use the identity. And the identity is this one down here. So if we look, let's see, how can I do this? It's so easy to go the wrong way, and then it jumps pages on you when you hit this small button. Ah, there we go. I'm trying to get it so I can look at it while we plug it in. Okay, that should be good enough. So our answer is 1 over p times everything here. 1/2 u, which is x. It'd be easier if I move. Hold on a second.
Is that a squared natural line divided by u, or what is that? With a vertical line there.
Right here, absolute value. All of that's in the natural log.
Oh, I see.
Okay, remember they use the absolute value whenever
Yeah.
you do the natural log. Okay, I'm confused. No, I'm not. Hold on. Gosh. Oh, no, I got it now. Okay, so hold on. Let's see. So based on theorem 8.2, okay, this 1/2, we don't have it twice. We just have it. In other words, that 1/2 right there is going to be outside our parentheses. And this 1 over p is outside our parentheses. So combining the 1/2 and the 1 over p, we get 1 over 2p times u is x, the square root of u squared plus a squared. Well, a squared, that...
What are u and a in here that we're...
Well, u is 2p, excuse me, u is x, a is 2p. Because we have the square root of 4p squared plus x squared. And remember, the variable always has to be this, whatever you're integrating by. In other words,
okay,
this du tells us that the variable is u, the constant is a. Okay, so the first thing I have is 1/2 times the 1 over p, so we get 1 over 2p, times u, that's x, times the square root of u squared plus a squared, which is x squared plus 4p squared. With me? Now we go to this term here, plus, well, a squared is 4p squared, times the natural log of u, that's x, plus the square root of x squared plus 4p squared, plus c, but the plus c isn't going to come into effect here. We're going to evaluate this thing from 0 to 2p. And we evaluate it by plugging in the upper limit into the variable. So I have 1 over 2p times x would be 2p times the square root of 4p squared plus 4p squared plus 4p squared natural log of 2p plus 4p squared plus 4p squared, that's 8p squared also. And without torturing the algebra too much, this evaluates, wow, I'm not sure, well, okay, now I can see where this 2p cancels that 2p. And this 2p down here is going to cancel with some of that 2p. So if you do the algebra here, you end up with 2p times the square root of 2 plus the natural log of absolute of 1 plus square root of 2. And they have removed the absolute value signs. Why? Because the natural log of 1 plus the square root of 2 is a positive number. So we no longer need the natural absolute value signs, and we can substitute parentheses for those. And that whole thing ends up being 4.59p. So the length of the arc from one end of the lattice rectum to the other is 4.59 times the focal length.
Sounds
The
good.
only thing I remember about this complicated algebra was how impressed I was when I investigated the way they proved what arc length was. They did very, very similar processes. Very creative that I don't think I would have thought of in 1,000 years. And they did it, and I remember how impressed I was with they did it. And now it kind of looks like you might have to do that kind of process on a lot of problems to solve for arc length. And the reason being is that the integral is 1 plus some function's derivative squared. And I remember also them saying that there aren't very many functions where if you take the derivative and square it, add 1 to it, and take the square root of it, that it's going to be very easy to integrate. In other words, it's almost always going to come out to be something that's virtually impossible to integrate. Not virtually impossible, but very, very difficult. Yeah, just because when you take the square root of 1 plus a function's derivative squared, you don't end up with something that looks very pretty. But you do end up with something that looks like one of these three things over here. The only thing is that we always have a 1 plus, and so you have to do all these algebraic manipulations in order to get it into square root of u squared plus a squared, as we saw here.
Now, where do we get the square root of 1 plus something?
That's the definition of arc length.
Oh, okay.
In other words, starting from this, S is arc length. Okay. So you're always starting, excuse me, there's an integral there. You're always starting with the square root of 1 plus some function. And the trick is to turn all of this stuff into something that looks like this. Or this, or this. Because then we know how to integrate those using these special integration formulas. Which we could work these out on our own using trig substitution. If you'll remember, when we integrated by trig substitution, we constantly were looking at this, because when you are integrating by trig substitution, you're talking about triangles and solving for, notice that this is how you solve for the hypotenuse of a right triangle. This is how you solve for one of the legs, and this is how you solve for one of the other legs. Is you take the square root of the hypotenuse minus the other leg. So trig substitution methods are what allow us to come up with these special integration formulas, and we use these frequently to calculate arc length, and not just arc length but surface area, because surface area is a function of arc length. You get surface area by starting with arc length, kind of like you get area by starting with the height of the rectangle. Okay. And we'll review all that stuff again sometime too. But I felt like it was time to move on to Chapter 10 at the moment. We didn't do any calculus here today that we haven't done in the past. We've done this before. So this, in essence, is a review. But coming up very quickly in this chapter, they do get into the calculus of conics and parametric equations. That's what's coming up, is calculus of conics and parametric equations.
Wow. Yeah, I still feel like my doing derivatives and integrals and stuff, I can't remember a lot of the stuff.
Well, that's okay. This book actually does a pretty good job of reviewing conics and parametric equations before they get into the calculus of it. So we'll have a natural review of both of those subjects.
Oh, okay.
Okay?
Sounds good, sure.
And let's pick it up next week from this point.
Okay, sure.
All right.
All right, sounds good.
Good one. Talk to you next week.
Okay, Dave. Talk to you soon.